So like I said out in the hall, I think we'll finish up chapter 12 today. We'll take the online test on Monday. We'll make that available all weekend after I get it done. I have to make it up, but I'll make it up either tonight or tomorrow morning. Then maybe not. It might be Sunday before I get it on there, okay, realistically. So look for it Sunday, so you can do it Sunday or Monday. I don't care. We'll have a time limit on it. You'll still do the fill in the blanks and then send me a copy of your work that you would show normally, and we'll all be happy then, since I won't be here on Monday. Okay? What else? Anything else we talked about out in the hall? Just in case somebody's listening to this on YouTube. I think that was about it, wasn't it? Yeah, that's where we'll be there. So otherwise, we'll finish up this talk about chapter 12. If I can find where I was at here. Probably right there. And why am I not seeing that on the screen? And we're going to skip over section 4 and just go to 12.5. Why? That's why. So in section 5, it talks about transmission of power by a shaft. I think it goes without saying, but I'm going to say it anyway. Typically, a rotating shaft is used to transmit power, and the applied torque is turned into work. So that's what we're going to look at today, to see how much work are we doing with a particular setup. So typically, work is defined as force times the distance, right? Here, you have to change the distance. The distance, instead of being this, let's see if I got let's just do it on screen. Come on. Interesting. Try it again.
We're skipping 12.4, we're doing 12.5 now.
That's correct. Skipping 12.4, going to 5. And I'm trying to get the slideshow to work. Oh, it's doing that. Daggone it, it's doing the it went through the time, didn't it? Okay, where is it? Let's see. I want to get to where I can get that out of there. Things all screwed up. Well, maybe I won't use the slideshow then. Oh, there it's coming. Okay. So there we go. Now we're back, and you can see that. Okay, so well, let's see. If I want to do any marking, I got to use this, don't I? So typically, then the work is where's my cursor? The work is taken care of force times the distance, and we're dealing with a linear type application, right? But now, since we're dealing with a rotating shaft, we have to look at it from an angular standpoint. Okay, so what we're looking at here is work is defined as torque. Okay, torque instead of just a force times an angular distance, and you use the amount of rotation on the angle. So you don't have to figure out a chordal length or anything like that. It's just the angle that thing is rotating through. Okay. If the shaft speed is constant, the work done in one rotation is equal to 2 times pi times the torque. All right. If the shaft speed is constant, so there's no acceleration or deceleration, then that's when you're talking about kinematics, right? That's another class you get to take, I believe, kinematics. It's where everything's in motion. So you'll be talking about different velocities and acceleration and such. Here you don't have to worry about that. So the equations you'll use, if you looked on, I didn't write that down on my notes, But if you look on, let's see, page 258, you'll see that power is a unit of work over time, and 1 horsepower is equal to 33,000 pounds-feet per 1 minute. Okay, so you'll have to keep that in mind. So yeah, power is work done over a time period. So work over time. Let's see what else here. For horsepower, the standard equation for that is going to be shown there in its equation 12.7 on 258. Horsepower is equal to the torque times the number of revolutions per minute divided by 63,025. So you'll probably end up having to use that. That's for English units. Okay? English units, and that's horsepower. For metric units, power is considered 1 watt, and that's 1 Newton meter per second. Now the equation for that is if you've got work per minute, you're looking at 2 times pi times the torque times the number of revolutions. However, note that the units that you're dealing with, since you're talking about metric units, they want you to convert that into seconds, Newton meters per second, and you have to divide that by 60. So keep that in mind. So that 12.7 SI is getting it down into seconds. Okay? That's pretty much all there is to that. That's why I wasn't too worried about time. But if we look at a couple examples, so example 12.10, calculate the maximum horsepower that can be transmitted by a 2.5-inch diameter solid steel shaft operating at 300 revolutions per minute. That's, everybody's clear on that? RPM, revolutions per minute?
Yeah, so they're using N sub R for RPM?
That's correct. Yep.
I'm thinking
Thinking that in terms of number of revolutions per minute. That's just the way I see it. Okay. Instead of putting in subscript RPM, they just use an R. Okay. So and the allowable shear stress for the shaft is 9,000 psi. So and honestly, you really shouldn't have to cheat on this test. There should be no need. This is just plugging in a bunch of numbers in it, as far as that goes. So as long as you're given enough stuff to go in there and figure out that'd be the only trick is, well, okay, what do I have and what do I need to get to? And what of those equations can I use? And I may end up giving you a little more time on this test just for that very reason, because you're going to have to go back and look at some of your other chapters potentially to remember some of this stuff. So I may open that up just a little bit more. Okay? But if you don't use it, it doesn't matter. So hopefully you won't need the whole amount of time, but if you do, we'll make it a little bit more forgiving. So the centroidal polar moment of inertia calculated. That's pretty self-explanatory. Pi times the diameter raised to the 4th power divided by 32. That one you're probably starting to get used to seeing a lot. So and when you're dealing with power, it's going to be typically it's going to be a round shaft. Could it be a square shaft? It could. It's not going to be typical, but you could have some kind of a square shaft. In fact, if you look at a power takeoff on a lot of farm equipment, for whatever reason, it is square. Because I know why. Because typically, the drive shaft that hooks up to the tractor, that hooks up to the implement, has to be able to slide back and forth. You have to slide it to get it on and off. And then when you're making turns, it has to be able to articulate as well. So they use square shafts, and then it can slide, and it can still transmit that power from the tractor to the implement. So there would be times when you very well could see that square situation come up. Well, then you're going to have to find your polar moment of inertia a little bit differently, aren't you? So that's all I'm saying there. It won't always be round, but more than likely it's going to be. And the other option is, if you're transmitting power like that and it had to slide, what would be your other option if you used a round shaft? You'd have to key it, wouldn't you? You'd have to put some kind of key in there to make sure those two round pieces don't spin, against each other. They'd have to spin in unison. So that would be your other option. That would be a machine design class where you'll have to go in and, you're going to have a cut in that shaft, right? So you're going to have to account for that. Even though you're filling it back in with the keyway, you still have a cut in there. So you'll be dealing with that. All right. So you find the polar moment of inertia. Then it says, using equation 12.3, the allowable torque can be calculated. And that value is the maximum torque. And so what are we looking at there? The allowable shear stress was given. Then we found the polar moment of inertia, and that was at the outermost part, right? 2.5 inches. And then the C is just the radius of that, right? 1.25 inches. I don't know why it has to be a C instead of an R. But whatever. I'm not the boss. I didn't make that rule up. So you find out that the torque is 27,600 pounds-inches. From that then, using the equation 12.7, the maximum horsepower is the torque, which we just found, times the revolutions per minute, which was given. And then the 63,025, that's your constant that's in there. And you find out that your maximum horsepower can be transmitted by that shaft is 131.4 horsepower. So, and there again, typically, like that RPM, let's go back to that tractor. On a tractor, typically, everything is rated at either 540 revolutions per minute or 1,000 revolutions per minute, depending on what your tractor is and what the implement is. That's just like this 300. That's something you're going to know. That's what it's set up to do. Now, you can go faster than that, and you can go slower than that. So there has to be some kind of a safety factor built in. Okay, well, we're going to set this at 540 RPM. That's our standard. But a lot of tractors can push them faster than that. So, just something you have to be aware of. So you would have that would be like a preset type arrangement. Okay? You know what your machine's going to run at. Now, how much power am I going to be able to generate with that particular shaft and it not fail? That's what you're looking at there. 12.11. We've got a hollow steel shaft. Well, the only difference here is we're going to have to take the two diameters that we raised to the fourth power and divide and subtract them out, right? So, and again, do that at like it shows here. So you find that. So we've got a hollow steel shaft, outside diameter 3.25, inside 3, transmits 280 horsepower at 900 RPM. Calculate the maximum torsional shear stress developed in that shaft, and then we would have to go and make sure that material can withstand that, right? So you do your polar moment of inertia, 3.5 minus the 3. Both of those raised to the fourth power times pi, divided by 32. You find out you got polar moment of inertia of 3 inches to the fourth power. Using equation 12.7, again, the torque developed. So you're just manipulating what you know and what you don't know, right? Can be calculated. Let's see. So you use that equation, manipulate that around, and you get the torque on one side. And let's see. Yeah, that's an easy one to manipulate that around, isn't it? The 63,025 was on the denominator side, so you have to put it on the numerator side. You switch it over, and then the revolutions per minute's in the numerator, so you switch that down to the denominator, and you end up with 19,610 pounds-inches of torque. Then your shear stress, torsional shear stress, is the torque times the radius divided by the polar moment of inertia. We know all that stuff now, don't we? Punch it in, you find out 10,620 psi of torsional shear stress on that shaft. So, okay, questions on these? All you're doing is manipulating that equation there at the end, right? And I think by now, especially even if you didn't do so well in your regular math class, by now you should be getting used to having been able to do that, right? Manipulate those calculations or those equations. You're supposed to be able to do that anyway, but it's like the beginning of the semester you were supposed to be able to do that.
There's no calculus involved here, so this is
Yeah.
great.
This is algebra, right? Type stuff. So, yeah. Okay, then let's see on 12 there. It's just, well, on this one though, we're looking at diameter, right? Determine the required diameter. You're given that you've got a 1020 steel, transmit power of 50 kilowatts. Speed of the shaft will be 6 revolutions per second. The allowable shear stress is 67 megapascals. The allowable angle of twist, which we didn't talk about that. So that would be the only difference there. But they're giving us the allowable angle of twist. So that's something they're giving us. That pretty much takes care of that. So basically you manipulate that equation. Now, do we have that? Is that equation anywhere? Probably not, is it? On the other diameter problems, I know we used, we did do some of that. Where was that equation? Let's see. Well, we did it in example 12.4, but now that example there gets a little bit more because we're going into the squared to the fourth. Holy cow. But basically it's just manipulating those equations. I'm telling you now, you won't see that one on test. Okay? If you do, you can smack me down on that one, because we're not going to deal with that at this point. That's pretty much it for the new stuff. So I won't give you any homework to do on that. You may have to do something like that on a test, but I think it'll be something you can handle. Okay, I'm not going to give you something you can't handle there. All right. Now, the homework. Sorry I didn't get that on there till this morning. Al sent me an email and I didn't check last night. I didn't check my emails at all last night. Sorry. I was busy doing home stuff, doing my homework.
I just like to write before I put it away.
Yeah, absolutely. Yeah, I understand, and I wish I'd have looked, but I didn't look till this morning, and then I immediately went upstairs and scanned them and put them on for you. But I apologize for that, but I was just being, like I said, I was just doing my homework.
But they weren't that hard. It's not like I didn't help you get them done.
Well, and that's the other part of it, I guess, that I didn't feel so bad about as far as that goes. So the only thing that I would say on those first couple, 12.1 and 12.2, it asks you to calculate, what the torque is at each of those sections. I don't know. The way they're showing it is a little bit different than what I remember. If I can find my cursor. Oh, let's see. I guess I better turn it on. Okay. What I remember is if on those shafts